last 3 years, I've been sampling and sampling and sampling in order to develop a sequential binomial sampling protocol that will turn into a rapid decision-making tool to help producers determine when they're above or below threshold. So far, we have developed the sampling protocol. I've tested it in the field myself, and I haven't come to a decision in more than 7 minutes. So when we say rapid, we mean it should be really fast. But then again, as you'll see in this, I've looked at a lot of sugarcane aphids over the last 3 years, so it does need some more field validation, but we'll get there. So everybody in the room, I'm sure, is familiar with sugarcane aphid. It was a huge issue, especially in Oklahoma in 2014, right after we had discovered it as a pest on sorghum in 2013. And then 2014, 2015 were really rough years. And then once we got into 16, we started leveling out. 17 and 18 have been, at least for North Texas to Kansas, we haven't had to spray nearly as much. And if we did, it was a one-time application versus I remember back in around 2014, 2015, guys were reporting spraying 4 and 5 times. So with the adaption of a little bit earlier planting date and some really nice hybrids, we've been able to avoid a lot of those applications. But I still think that Oklahoma producers as a whole are a little jumpy, a little gun shy when it comes to sugarcane aphid and might be pulling that trigger a little too soon. So hopefully this sampling protocol not only rapidly helps producers determine when they're above threshold, but also when they're below and when they can rest well at night and come back and monitor a population and it's not so tedious and overwhelming. But you know, anybody who's grown it in this room knows what sugarcane aphid can do to your plant. If it was early planted, you're looking at harvestability issues. If it's late planted, you're looking at yield loss when it infests in early vegetative. Okay, so we've really had a gambit of different sampling protocols come through since we started off as an emergency situation in 2013. So of course everyone jumped to action to try and help some sort of monitoring happen, and that's kind of where this first protocols, I should say, were coming out, where no one had really agreed on what the threshold was, and we knew it was different for every state, and we knew it was different depending upon those growers' needs and those kind of things. And so when you review the literature for extension sites from Kansas to Georgia, you see that there's a threshold of 25 to 150 sugarcane aphids per leaf, and that's kind of what people were trying to sample for. And when you were trying to sample for that way, what you'd have to do is take 40 plus samples where you would keep track of how many aphids were on each of the 2 leaves that you sampled, which was an upper and a lower, on 40 plus plants, and then you add those all together, divide it by how many samples you took, and then times it by 100 to see if you were in some sort of percentage or if you just took an average per leaf and it fell somewhere in these largely observational thresholds that were set during that time. And so it was really, we've determined that these earlier thresholds are still fairly accurate, surprisingly enough, but the sampling protocols used to determine them were not helpful, I could say that. So then recently in the High Plains, there was a really nice study put together where she determined a threshold and then made sampling recommendations based on her plot trials. And one thing that's important that we need to be able to differentiate is what a sampling protocol looks like versus determining an economic threshold. I don't determine economic thresholds. That's a yield relationship to number of aphids per leaf or per leaves. I don't do that. I develop sampling protocols to know when you're at that threshold. So think of me more as a ecologist, you could say. I sample and I use models to determine how to sample a pest in an environment. And so when you confuse those, you largely end up with sampling protocols that were built on plots that included susceptible hybrids, and you start to come up with methods that may not be applicable to 40 acres or larger, plots of land. Additionally, even in her sampling recommendations, you're taking 4 stops of 10 plants. So you're still taking 40 samples of 42 leaf samples, 40 plants. And that's a lot of sampling. And it still requires math to determine what your average per leaf was. And then lastly was John Gordy and Dr. Brewer's most recent protocol, which is a binomial sampling protocol that's very similar to what we found in our research as well. And it's the presence-absence of 50 aphids, and you look at 40 plus plants, and then you determine if 20 or 30% of those had 50 or more aphids, and it gives you a threshold. But the problem with that is that it's not a sequential sampling protocol, so it doesn't really give you stop lines. You still take 40 samples, whether you were above threshold 30 samples ago, or if you knew you weren't going to need to sample anymore 30 samples ago, you still take 40. So our job not only incorporated a much larger data set, because we did a lot more, we sampled a lot more states than just Texas, but it also was validated, and we had stop lines so that you know when to stop sampling. So we would still argue that until this research protocol is published, there is still no published research-based scouting tool that can be used. So that was OSU's job. It was a multi-state collaborative, a giant grant that was put together, and our job was to characterize, develop, validate, and deliver a sequential binomial sampling protocol. And you do this by designing a sampling plan. And sampling plans are not easy to do. It's a lot of modeling, and it takes a long time. And that's why those sampling protocols that are fast and dirty based on observational was so necessary when this was still an emergency, when this pest was, just coming out. But now that we have spent some time, I think that we should move forward with a sampling protocol developed in this way. And how you start is you sample to know how to sample. So we developed a stratified sampling protocol that puts a sampling universe into a grid system where we can extract a lot of information about how the sugarcane aphid is distributed within a field and within a plant. Then you categorize that species of aphids aggregation type. We use ecological laws for that, specifically Taylor's power law, which is an empirical model that assigns an aggregation factor to each species. And we'll go over all that as well. And that helps us to know not only how to sample, but approximately how many samples we're looking at taking. Then we describe the within field distribution based on a nested ANOVA approach. It's a telescoping approach where we start big with state-to-state comparisons and go all the way down to within canopy comparisons. Then we define the best sampling unit, and that's trying to predict where the aphids are most often found on the plant and how many of those we should take. So in this case, it would be leaves and how many leaves to take and where we should take them. Determining a tally threshold. So with an aphid that's 22 micrometers long on a sorghum leaf that can be every bit of 2 feet long in boot stage, there's not a lot of precision in saying whether or not there's one aphid or not on that leaf. So a standard presence-absence model, whether that says yes, there's an aphid or no, there's not, is not very accurate for something so small in, not even on how big that leaf is, but in 40 acres or so. And so we need to define a number of aphids that relates well, has a strong relationship to the mean number of aphids per plant, that's easy to see. And so that's a number of aphids that we can say, this plant is infested, it's easy to visualize, and move on without having to count. And then you take another ecological genius, which was Wald in 1971, and he developed the sequential probability ratio test. And that set of equations allows us to develop stop lines. So how many need to be infested with with X amount of aphids before we've met a threshold, a said action threshold. So I'll show you those as well. And then lastly, we validate it using another modeling software, and we'll also validate it within the field. And then we get to where we are now. We're ready to give you something that's actually usable after all these models. So that's kind of what I'm going to walk you through now. So this was our stratified sampling protocol. This was for research only. And what it allowed us to do was to look at a 90 meter by 90 meter sampling universe. There was 9 30 by 30 meter cells within that sampling universe. And then within each cell, we took 2 samples of 3 plants in a row, an upper-ish and a lower-ish leaf. And then within each column, we randomly selected 2 plants from each column that were completely enumerated for aphids per leaf, starting from the bottom leaf all the way up to the flag leaf in most situations. And so the results from that was that we actually ended up building this model based on 134 sites across Kansas, Oklahoma, Texas, and Arkansas. Within those sites, we were able to do 281 sampling events. And if you think about each sampling event having having 54 plants, we sampled more than 15,000 plants across a growing season for 2 years in order to develop this sampling plan. In addition to that, those randomized plants that got completely enumerated, every leaf, we ended up with 1,644 of those plants that we used to define trends of where within the canopy is most predictive of the plant total population of aphids. So then we moved on to step 2, which was that aggregation factor I was talking to you guys about with the Taylor's power law, which is that empirical model that assigns an aggregation factor value to each species, in theory. But what we found was that these aphids colonized so differently in the southern states. For this model, it was South Texas and Arkansas, that they colonized that area so much different than they colonized North Texas, Oklahoma, and Kansas, that they statistically had different aggregation factors, significantly different aggregation factors, which is interesting because according to Taylor's ecological law, each species is supposed to have one aggregation factor, but aphids always seem to supersede that law, and both green bug and sugarcane aphid end up having two different colonization or aggregation factors. So that was really interesting. And you're saying, what does this mean? Because that's not even that big of a difference. Well, it means a lot when you try and calculate an optimum sample size, how many samples you need to take in order to understand how many aphids are on a leaf average within a 40-acre field. And so at a 10% precision level, the northern region needs to take more than 1,000 plant samples to accurately estimate or precisely estimate whether or not you have a mean of 50 aphids per leaf. And in the southern region, that's clear down around 300. That's still way more plants than we'd ever want to sample, but that gives a little context to what that aggregation factor really means as far as sampling context. And so when you look at numbers like over 1,300 samples, it was about right now that we determined that an enumerative sequential sampling protocol was not possible. We're not, with precision, going to be able to tell you how many aphids you have in your field, but we can, with precision, tell you if you're above or below a certain threshold. So now that we know about how many samples we would need to take for that and how clumped they are, we need to figure out how to sample that field to find these clumps. And that's where we use that stratified sampling protocol. We ran a nested ANOVA, nested analysis of variance, which allows us to figure out what the percentage of variance is accounted for within that sampling protocol, the stratified sampling protocol that we did. And in the northern region, interestingly enough, we found that more than 70% of the variance can be accounted for just by taking those 3 plants in a row, which tells us that they are so aggregated that one plant to another has the highest amount of variance in that field. And that's a really incredible concept to think about when we think about how to scout and detect, is just to say that between one plant to another plant, you can have 73% of the variance within that field. When you add in this other 12%-ish, you start to get around 85% of variance accounted for by taking those 2 samples of 3 within a 30-meter radius. And of course, up here, this just says that we would sample each state individually. We're not going to say we're at threshold in Kansas, so let's spray all of Oklahoma. And that we need to sample each field individually as well, which we would always do anyway. But what's really curious is that in the northern region, which is North Texas, Oklahoma, and Kansas, there was no variance accounted for between columns or cells, which means the depth into that sampling universe or how wide you sample didn't matter. What mattered in Oklahoma, Kansas, and northern Texas is that you sampled 3 plants in a row and you took each of those 3 samplings, consecutive samplings within 30 meters of each other. Isn't that surprising?
Okay, I sprayed field A, I better go spray B too.
Or I didn't spray and I don't need to spray. But yeah, it was shocking. And this is 3 states went into this, and to only have 2% variance between 3 different states, that really gives you a good idea of how they're colonizing, how they're coming in. Dr. Elliott could probably speak better to, those small parcel droppings from atmosphere, but they're definitely not flooding in like the way they do from College Station south, which is what we're going to look at here. So in the southern region, as we kind of suspected based on that aggregation factor being significantly different from the northern region, we can see that those two samplings of 3 within a 30-meter radius accounts for 35% of the variance, and you know, you can get 55% of the variance total by sampling the, you know, 3 plants in a row within 30 meters of each other. But what's interesting is that in the southern region, where you sample starts to matter. And so, you know, based on observational data and talking with producers in the southern areas, this could be where we can see statistically that edge effect, where they're coming in early in the season off of Johnson grass and kind of inundating a sorghum field along the edge. And so where you sample in the field, so making sure that you're actually starting at an edge and moving in and across in that 90 meters is important in the southern region. So that tells us that we need to sample differently depending upon where you are. And their between states was 0, and that's between South Texas and Arkansas. But their between fields was really high. And so as long as we sample each field individually, and we start at an edge and we walk 25 paces every time we take a sampling of 3, we should be able to account for all of this variance. So now we know how much to, roughly how much to sample, how to sample, where to sample. We need to define our sampling unit. And so we already knew that there were threshold relationships between 2 leaves and the yield. And so we decided to figure out, okay, if we know that roughly 2 leaves are important, where should we take these 2 leaves? Because previous literature and extension had said you take the uppermost and the lowermost leaf. Well, we decided to test that theory with those 1,644 plants that we had counted from top to bottom and knew the total amount of aphids per plant. So we broke it down into the upper 2 most leaves, the lower 2 most leaves, and then everything that was in the middle we called mid-canopy. And what we found is that even considering growth stage, state, and year, the middle of the canopy was the most predictive of the total. That tells us that those leaves below those upper 2 most have the most aphids and can predict the total amount of aphids per plant the best. And the other important thing to think about that is then we broke that study down into growth stage to see what part of the canopy was most important by growth stage. We broke it down by state, and then we broke it down by growth stage and state. And I'll show you just this next one because those charts get really long, but overwhelmingly the middle was the best model. So it doesn't matter how many ways you want to chop up this data, that middle part of the canopy is the most predictive of the plant's total. So from that we can say when you're sampling your 3 plants in a row 30 meters from each other in a U shape into your field, take 2 leaf samples from the middle of the canopy. So then it's time to figure out what we're going to use as our presence absence because no one wants to count every aphid on a leaf. I don't anymore. And I know that most of my producers don't. And so what we did was we actually ran, this is a small subsample of all the different models we ran to figure out what number of aphids is most predictive of the mean per plant. And it ranged from 1 to 250, and it was over like 20 different thresholds, tally threshold regression analyses. But these were the best contenders we had. And to develop this, we actually limited the data set to only fields that were an average intensity per plant of 215 or less. And I'll tell you why, and it was because those fields that were, 500 aphids per plant to 3,000 aphids per plant are well above any established economic injury level, let alone economic threshold. And so when we're establishing a good sampling protocol, we don't want to worry about those fields that are obviously needing to be sprayed. We want to help people make management decisions when they're below threshold or right about at threshold. Those are the sticky situations. Those are the ones when, timing is really crucial before yield loss. And so these were the models that we kept. And so we kept presence or absence of 150 and 160 because they were the best fit models. But thinking about application purposes, I know I couldn't tell the difference between 150 and 160 aphids on a plant. And so we also continued with 50 aphids because that's a really nice number that everyone seems to visually recognize. Is this more than 50 aphids? And 100, because those are easy to process numbers for everyone. To further that point, though, of why we furthered development with the tally thresholds being 150, is because when you put together the data sets and you make a nice simple little scatter plot of the average number of sugarcane aphids per plant. So this is a potential threshold area, economic threshold area, and how many need to be infested with 160 or more in order to hit these thresholds. Say 100, you're just over 10% need to be infested with 160 before you're at that action threshold. And so based on these, we're based on a 54 plant model. That's what 6 or 7 plants you need to look at before you've made a decision for your entire field. And as an entomologist and as someone who builds sampling plans, I'm not comfortable with that. All the literature says you need to have a minimum sample size of 10 plants at least to make a precise decision. And so with you being, at or above threshold and only 6 plants theoretically, that's just not enough. Versus when we go up to this presence or absence of 50, you go to that same 100 aphids per plant threshold, and you're at 30% infested, which ups the number of plants you've looked at. It lowers your error, increases precision. That's a safer bet, and that's why we discontinued these higher tally thresholds and move forward with a presence absence of 50 or 100. So once you've decided what threshold you use, this is when we used Wald's SPRT equations to design stop lines for sequential modeling. And so this is kind of what the sampling protocols look like before they're a deliverable for everybody. And we picked 4 different action thresholds or 4 different ETs for each sampling protocol. And so this is a action threshold for 20% infested with 50 or more. And it goes all the way to 50% infested with 50 or more. And these relate to 150, 100 aphids, or 150 aphids per plant, 100 aphids per plant, 75 aphids per plant, and 25 aphids per plant. And our reason for doing this is, one, because we want to develop a sampling plan that's good over multiple states, from essentially Mississippi to Kansas, but we also wanted a sampling protocol that could be integrated into whatever ET and yield goals that the producer had as well. It has to be dynamic. You can't just make one sampling protocol and expect it to be across multiple ETs. But these are pretty strong for any economic threshold that we could find from Georgia to here. And the same thing with 100 sugarcane aphids. So then we need to validate it. So in order to validate this sampling protocol that we developed, we used 50 externally sampled fields, ones that I didn't sample, from Kansas, Oklahoma, Texas, Mississippi, and Louisiana. And to put this into perspective, these were almost identical ranging in number of aphids per plant. We had anywhere from 0.1 aphids per leaf to 3,000 on average aphids per leaf. So it's a very representative data set. And this sampling data that we use, the sampling model that we use, takes those externally sampled fields and samples them virtually 500 times each, and comes up with an average sample number it took to determine a action, whether that was to treat or not to treat. This protocol is for not to treat. So this is the average sample number across, all these action thresholds, and with an error rate of 10% and 5%, remarkably all had around 11 samples to determine not to treat. And likewise, this model gives us an operation characteristic, which is really a probit analysis to allow us to know the probability of not treating. And in most cases, at very least, it's above 70% of the time you would not treat based on the 50 fields that we validated with. So that lets us know that using this sampling protocol within 5% error rate, you can safely know when you need to treat or not. And even though these fields, a lot of them were, some of them were above threshold, 70% of the time you're not treating. So I really think this protocol of presence-absence of 50 aphids will really help us to not pull the trigger when we shouldn't. So this is what the deliverable starts to look like for producers, is we take those stop lines and we make it into more of a graphic type situation where they can see when to stop sampling based on number of plants, inspected, and number of plants with 50 or more. And so say you sampled 17 plants, and if out of those 17, less than 2 were infested with 50 or more, you're done sampling. If you sampled those same 17 plants and 8 of them were infested with 50 or more sugarcane aphids, stop sampling, it's time to treat. But if you fall somewhere in this middle zone, we'll say you had 5 samples that had aphids, more than 50 aphids, you would continue sampling until you met a treatment decision. And if that's too confusing, we actually made it into a in-field tool that you can use. And so what we do here is you got 3 stars, so those are your 3 plants in a row that you're going to sample at every stop. And if you take 2 leaves and you look at them simultaneously and you say, is this above or below 50? If it's below 50, you're going to strike one of the stars next to that stop. If it's above 50, you're going to circle it. When you get down to stop 4, which ends in 12 plant samples, you're going to add up how many circles you had, so how many plants were infested with more than 50 aphids, and it'll give you a decision based on that. In personal experience, I've never made it past 13 to 15 samples, and that was in a field that was really close to threshold. Yes, and it's crucial that you look at 2 leaves together, and I'll give you the scenario of why. So if you were to look at 1 leaf and say it's at 15, and you say that's well under 50, throw it on the ground. You look at another leaf and it's like 40 something, but it's under 50, so you throw it on the ground. It visually looks less than 50, so you throw it on the ground. That plant technically was a circle and you just put a slash through it. because you didn't visualize it as above 50. So looking at those leaves together and saying, yes, this is above 50 is very important. For example, just for reference, 50 aphids is about the size of a quarter in most situations, about that big. So if each leaf has about this much, or if one leaf has, you know, a big chunk of aphids and the other one has none, that plant is still infested. I would go ahead and pick it. And here's why, is because I spent the last 3 years being so careful about not being biased on what leaves I picked. I know that this sampling protocol will work out in the wash, and you want to pick the leaves that are most indicative of how many aphids are in your field. It would work out, and this is why, is because say you get to a field, you're on the edge, and you see a shiny leaf, you go straight to that plant. Based on my data, I know for a fact that the 2 plants next to it are not going to look like that plant. So you're going to sample that one, you're going to take that one shiny leaf, the leaf right above that one shiny leaf, it's obviously going to be infested. You're going to circle that one, go to the plant right next to it, it might be infested, it might not. Go to the one next to it, it might be infested, it might not. And then sure enough, if you walk another, you know, you're 25 paces into the field and stop, it is more random, but what I'm saying is that even if you get to your next spot and you deliberately pick the next plant that's covered in aphids, the 2 next to it are not guaranteed to be covered in aphids, and we know that based on that data. And so if you want to play this game of one every 3rd stop is infested, I mean, you can, but you'll be sampling clear into these numbers because you're not going to get to that sampling threshold by picking those ones, by picking those super infested plants. Because if you're below threshold, it'll be really hard pressed to find more of those plants to the point that it gives you a stop and treat. 5% error rate, it will work out, even if they decide to be biased in sampling. It is currently being worked into as an app that doesn't require internet, and all you're going to have to do is, you know, is there 50? Yes, yes, no, yes, no. And then a red screen will pop up and say treat or stop, you know, stop, treat, stop, don't treat. Super easy. We're integrating it into a collective glance and go app that's going to include green bug as well for wheat. So anything that's sequential binomial, we're going to try and put it together into one solid app. But for now, I do have one of these out on our extension website that you can print and use. But by the time we get really rolling in the sorghum season, we hope to have all of them out at least on paper, and then the app will definitely follow, because you're exactly right. It's super easy to integrate into that, and everyone has their phone on them. So absolutely.